I'm Jihyeon, a member of the KGSEA Math Circle, and today I'll be talking about hypothesis testing for discrete probability. To start with the basics, what is discrete probability? It's one that counts occurrences that have countable or finite outcomes, and this contrasts with continuous probability that you may already know of, where outcomes can fall anywhere on a continuum. So to talk about discrete probability today, I'll be using the calculator TI Inspire CX2, but you can use any others that have the statistics and probability functions. To put this in context, think about randomly guessing on a test, where you have a multiple choice test with options A, B, C, and D. What is the probability that you get 1 out of 2 correct, 3 out of 3 correct, or 30 out of 50 correct? To guess this, you might be thinking about the combinations of the questions and the probability 1/4 or 3/4. This is an example of where you can use a binomial experiment. And here are the characteristics. In binomial experiments, there is a fixed number of independent trials. There are only 2 possible outcomes, which are success or failure, which will be defined, and the probability of success remains constant. What I mean by this is this. Here's the null distribution for binomial distribution, where random variable x has a binomial distribution with n number of trials and probability of success p. And on the right, you can see the equation for the binomial probability. However, note that we will not be using this equation manually. Instead, we'll be using a calculator to find the probability itself. Also, do note that in the null distribution, the number of trials will stay discrete, so only positive integer values are applicable, but p, the probability, is continuous, which means that it can be a real number between 0 and 1. So in terms of using technology to calculate binomial probability, let's use this question. Given the random variable x with binomial distribution with n 12 number of trials and a probability of 0.6, determine the following. On your calculator, you might have a function saying statistics or probability. And from there, use the function binom PDF with n the same, p the same probability with the x value that's given, or binom CDF with n, p minimum and maximum. PDF is for particular probability distributions, or the CDF is for cumulative. So binom PDF will be used for question A in this case, and CDF will be used for B, C, and D. You can take some time to answer these questions, but I'll move on to the answers. So the first one, if you use the calculator correctly, would give you 0.227. B will be 0.335, C 0.0195, and D 0.759, given that you have used for the binom CDF 12, 0.6, 4, and 8, where the min and max are inclusive. Let's practice more binomial probability. First, you have to notice whether or not you have or can use binomial distribution. With the first question, it reads, a coin is biased so that the probability of a head is 0.74. The coin is tossed 7 times, and A is the number of tails. Find probability where A equals 5. First, since we have a fixed number of trials, 7 times, and the given probability of a head, 0.74, and A is the number of tails, you can quickly realize that the probability for tails is 1 minus 0.74, which is 0.26. And using the calculator, you should have received binom PDF 7, 0.26, and 5. So the answer should be 0.0137. The second question reads, a bag contains 61 white marbles and 47 red marbles. A marble is selected at random and is type noted, then discarded. This is repeated 5 times, and B is the number of red marbles chosen. 5 probability where B equals 4. Well, first, as I said, think whether or not you can use binomial probability for this case. And the answer is no, because the probability changes as the marble's type is noted and then discarded instead of being replaced. Another question, a tin contains 10 milk chocolates, 1 dark chocolate, and 7 white chocolates. A chocolate is selected at random and its flavor noted and replaced. This is repeated 12 times, and C is the number of white chocolate recorded. Find probability where C is less than or equal to 6. In this case, you can use binomial probability, and you will be using binom CDF with 12 number of trials, probability of 7/18, because 18 is the total number of chocolates in the tin, 0 being the minimum and 6 being the max, with the answer 0.861. Now I'll be talking about hypothesis testing and give you a list of definitions that you will have to know in order to follow along in the presentation. So a hypothesis is a statement about unknown parameters or distributions. You may have heard of the term hypothesis in other science subjects, but here we'll be discussing hypothesis for statistics. H0 is null hypothesis, and it assumes that results are independent. On the other hand, H1 is the alternative hypothesis, which assumes that results are not independent. So in other words, we would accept alternative hypothesis if we reject the null hypothesis. The p-value is the probability of obtaining the observed results, assuming the null hypothesis is true. The significance level alpha is the criteria for retaining or rejecting the p-value and hence the hypothesis, because they're, as I said, interlinked. When p-value is greater than the significance level, you don't reject the null hypothesis. But when it's less than the significance level, you would reject the null hypothesis. And the critical region, which we will delve deeper into in the following slides, is where it's the sum of x values whose cumulative probability is lower than the significance level, because that's the criteria. How can we find the critical region? So in this case, for what values would you reject the null hypothesis? The null hypothesis is where p equals 0.5, alternative hypothesis when p is greater than 0.5, significance level of 0.05, in other words, like 5%, and we'll have 10 number of trials. So first, you have to note that it's a one-tailed test, meaning that you will only look at one side of the distribution. And since it's greater than 0.5, you start from looking at the top and realize in the 10th trial, the probability is 0.001, and the next sum, when you go to the 9th, is 0.011. But for the 8th one, the sum equals 0.051, which is greater than the significance level alpha. So you can realize here that 8 is not in the critical region. But you may ask that this is such a manual labor work, and you might want to use a calculator. Therefore, on the calculator, what you can use is function inverse binomial. And what you write here is the cumulative probability, the number of trials, and the probability. And then you will get 8. And how you can interpret it is that that's the area where the critical region cuts off. So the critical region would be from 9 up and up. In the other case, for what values would you reject the null hypothesis? Again, note that it's the one-tailed test, but it's where p is less than 0.5. So looking at the left-hand side from this distribution table, you realize that up to 0, 1, and 2, the cumulative probability is 0.051, which is less than the significance level. And till the 3rd, the cumulative probability is 0.171, which is greater than the significance level, so it's not going to be in the critical region. The last case is this. So where the alternative hypothesis is where p does not equal 0.5 instead of being less than or greater than 0.5. The significance level here is 0.1. And what you have to do first is realize that it's a two-tailed test. So you'll be looking at both the upper hand and the lower hand, which means that you also have to divide the significance level into half, which will give you 0.05 or 5%. So on the left-hand side, this is what you get. And you do the same thing. So up to 2, the cumulative probability is 0.051, which is greater than half of the significance level. So it's not in the critical region. And the same goes for the right-hand side. Here's an example of critical region in a binomial distribution. Mary and Kevin are playing a dice game. Mary has to guess the maximum number of times 6 shows up in 30 rolls. If the number 6 shows up that many times or less, Mary wins. And furthermore, the smaller the number that she guesses, the greater her winnings. What is the smallest number Mary can guess if she wants the probability of winning to be at least 77%? The null distribution in this case will be the random variable x will have a distribution with 30 number of trials and 1/6 because there are 6 sides in a die. And we're looking at the probability where the probability is greater than 77%, so 0.77. And on the calculator, if you use the inverse binomial function, you will get 6. And now you can know that the smallest number that Mary can guess to win will be 6. Another discrete probability distribution that I would like to introduce is Poisson distribution. It's when measuring how many successes take place within a given interval. So here are some examples. Number of cars that drive in front of school every hour. Here the success criteria is a car driving in front of school, and the interval is hour because you're looking at every hour. Another example is the number of the alphabet A per page in a book. Success is the alphabet A appearing, and the interval will be page in a book. This is the measure of the Poisson distribution. Similarly, you can find the null distribution, and let's say that random variable x has a Poisson distribution with lambda. And here, lambda is both expected value and variance, and they are equal. On the right-hand side is the equation, yet we will not be using that. Other characteristics of the Poisson distribution include that lambda is uniform across all intervals, and occurrences in a time interval are independent and don't occur at the same time or position. How can we use our calculator? It's very similar to binomial distribution. We use PDF and CDF, PDF particular value like the question A, and the CDF for cumulative probability. And the questions answer are as follows. And for C, you should have entered Poisson CDF 2.9, the expected value and variance, and then 4 up to 8, so min and max. When testing for Poisson distribution, there's something that you have to be very mindful of, and I'll use an example to illustrate that. Just in place basketball, the number of shots he takes during any 6 minutes of play in one game can be modeled by Poisson distribution with mean 2.5. After months of practice, he wants to know if the training helped him improve. The null hypothesis is the lambda is 2.5. The alternative will be that it's greater than 2.5 because you want to see if he improved, which in other words would mean that he can make more shots than 2.5. Then his coach records the number of shots in a 6-minute plays on 5 games, and the total count is 15. What you should realize is that the observed rate is not expressed in the same time frame or interval as the original one. So the observed is from 5 games versus the given in terms of 1 game. Therefore, you must express lambda in terms of the rate of observation. What I mean by this is that you have to create a new one where you multiply 5 with the original mean of 2.5, and that will give you the test statistic, which is 12.5. And now you have a new null distribution, x variable with the Poisson distribution 12.5. And when finding the probability, you will look at where probability x, the random variable x, is greater or equal to 15, and the answer will be 0.327. Let's practice more Poisson probability. An ice cream business counts how many kilograms of ice cream they sell per day. Assume that they sell on average 2.31 kilograms per day, and that the kilogram can be modeled by random variable A with a Poisson distribution mean 2.31. Find the probability that the business sells 0 kilograms in a working week of 5 days. Here's what you have to do. First, you can use Poisson with probability where 5A equals 0. Because you're looking at 5 days, and on average per day is given on the interval per day, and that's why you'll be multiplying. But here's another way you can solve this problem, which you will have to apply your knowledge about binomial distribution again. First, you can find a probability where A equals 0 because you're looking at 1 day, and then use the binomial experiment to see where 5 days is 5 number of trials, and you use this probability given from Poisson in the binomial probability, and that will give you the same answer. In another question, look at this. A city planner believes that the number of Starbucks in Seoul per block has a mean of 0.2. It is known that the number of Starbucks per block in Seoul follows a Poisson distribution. The city planner's assistant, however, believes that there are more Starbucks in Seoul than that and goes through 50 blocks to find a total of 12 Starbucks. At 10% significance level, what is the conclusion to this test? Well, this is a long, and you can follow this step by step and take some time, but I'll move on to the answers. First, the null distribution is the lambda is 0.2 because I said the mean is 0.2. The null hypothesis, the alternative hypothesis is that it's greater than 0.2, which is what the assistant believes. The significance level is 10%, so 0.1. However, since the assistant went through 50 blocks instead of 1 block, which is where the mean of 0.2 is received, you will have to create the new test statistic, and that will be 10. Now, to find the probability, you will use where probability of random variable x is greater or equal to 12, and the answer is 0.303. However, now what is the conclusion to this test? The conclusion is that we retain the null hypothesis where the mean is 0.2 because the p-value is greater than 0.1. The p-value is here what we received, 0.303. And in other words, there is insufficient evidence to show the mean of number of Starbucks per block in Seoul is greater than 0.2. Now, in this presentation, I covered what discrete probability is. We talked about binomial and Poisson distributions, using a calculator to solve probability questions, hypothesis testing, and finding the critical region and conclusion of tests. What you can do further if you're interested is find type 1 and type 2 errors in terms of discrete probability and other types of discrete probability, including as you can see on the list, as well as continuous probability. With that being said, that's all for the discrete probability and hypothesis testing in this presentation. Thank you for listening.